Hey, everybody. I'm just posting the final notifications. Cool. So you should all have the machine learning pre-course GitHub repository. If you pass all the tests in the machine learning pre-course repository, then you will greatly improve your chances of being accepted into the Lambda School machine learning course taught by yours truly, with coursework having developed by yours truly for the full-time and the part-time class, both starting on April 2nd in 2 weeks, 2 weeks from Monday. So get your pre-coursework done and submit it if you're hoping to join. Let me get that link to share with those of you who are watching on YouTube. And I will share the pre-coursework with you as well. Hey, everybody. There's the link to the Lambda School Machine Learning course sign up. Find the Slack channel. Only 9 Chrome windows down. Here it is. We're looking at giraffes, yep, and goats, Slack channel. So you're really missing out if you haven't signed up yet for that. People in Slack are asking about the video link, so I'm going to prepare that for them as well real quick. And then we will get started. I see goats, I see giraffes, I see linear algebra. All right. I believe we are prepared to get started. Welcome to the last day of the Lambda School Machine Learning Mini Bootcamp. The purpose of the last 4 days of instruction have been to give you some sense of what the machine learning coursework is going to be like at Lambda School. If you didn't get my background on day 1, I completed all the PhD coursework in artificial intelligence and machine learning at Colorado State University. I graduated in 2008 with a master's degree, and I walked. The reason being that after having spent 4 years studying artificial intelligence in an academic setting, the main impression that I got was that I had 7 years of grad school left to get the PhD, and it was going to take 16-hour days in order to produce enough material to be competitive with other graduates, because that's pretty much what people in grad school are doing, are working 16-hour days and producing as much as they can. And then after graduation, I would have to work another 7 years of 16-hour days in order to receive tenure at some university. And hopefully I'd have, something on the order of 35 to 55 publications at that point. And I'd have a few different data models that were found to be state-of-the-art and that no one else had come up with. And it didn't match the reward. The academic level of labor didn't match the reward in my mind. So I went to industry. I've been building mobile apps and doing data science and numeric analysis on the side whenever a good opportunity arose as a consultant. and now I teach for Lambda School. I built our computer science curriculum, which is now being expertly handled by computer scientists who are more talented than me. And I've moved on to our machine learning curriculum, which I hope to share with you all in 2 weeks from Monday. Instead of creating machine learning models, I create biological learning models, and hope that they will create better models than me going forward into the future. Somebody asked, I believe that it's been covered. Here's the URL for GitHub. Yeah, so no, Eric, that is for tonight. That's right, they're the same. If you have done the ML pre-course GitHub repository to fullness, passed all the unit tests, and then submitted that to me via a pull request or pushed it to the repository via pull request, then you're finished. And I'll pull your repository over this weekend. I'll run the tests that you're supposed to have satisfied, and everybody who gets a 100% pass automatically gets elevated into the top of our application stack. So if you've done 100% acceptance, if you've done 100% unit test pass, sent me that pull request, you should expect to be receiving an acceptance into the program soon. Thank you. Thank you for your kind words. So for tonight, we're going to talk about linear algebra. Linear algebra is mathematics that involve the relationship of coordinates in space and what you can do with them and what they mean. I can't dive into linear algebra really without talking about data first. And there's a substantial portion of the main coursework involving data and what it is and what to do with it. As a machine learning engineer, your biggest job is data prep. Your second biggest job is algorithm implementation, which is something that you're going to be given for free because there are amazing libraries out there that have done all this stuff for you most of the time, but you're still going to have to tweak them, and they're not going to work right, and you're going to have to labor with your code to get them working. And then finally, the third thing you'll be doing the most of is reading new papers and trying to capture new research so that you can apply that to the work that you're doing, whatever it is, professional or industrial, or building up your portfolio. But back to the first thing you do is data prep. And that's because data is messy, it's noisy, it's varying, where one piece of data carries more apparent information than another piece of data, even though that's not actually true once it's been fully prepared. So you spend a lot of time looking at data, and what data is a matrix. And a matrix is a term from linear algebra that is a two-dimensional grid of numbers, which you have all seen before, I want to bet, in an Excel spreadsheet or some other kind of spreadsheet. And that data actually represents mathematical relationships of points in space. And so that's what we're talking about today, is linear algebra, the basic arithmetic for manipulating, modifying, and interpreting points in space. And we're not going to get in particularly deeply with it. There's a lot to learn with linear algebra. There's, entire subfields of mathematics about it. But I want you to be able to look at a spreadsheet and understand that the whole spreadsheet is just a cloud of points in a big space. The space is the number of columns in the spreadsheet. That's how many dimensions it has. And I want you to also understand that you can pick any two dimensions from your spreadsheet and draw a graph of them on a piece of paper. Just very trivially, you could write them out, because a column of data in a spreadsheet is a line in a graph, like we were talking about yesterday, right? What is a function? What is a point? It's just a number on a line in a graph. And if you've got two numbers together, that's a point on a two-dimensional graph. So I think I've talked to you long enough without drawing you pictures. I ordered a larger Wacom tablet because, honestly, I love writing on whiteboards. I always have. And I'm going to improve my whiteboard writing skills by getting more precision. Okay, so just like yesterday, I'm just going to screen share with GIMP. I remember 1200 by 700 was bigger yesterday. Try a different size. Close this. Maybe it was 1600 by 700. That's kind of funny. I definitely remember it was bigger yesterday, but that's okay. All right, and then I've got to get my tools lined up. Pick my pencil. And I don't like size 20 at all. Go down to size 8. Everybody can hear me fine? Presentation's going smoothly so far? Nothing that I'm not paying attention to? All right, so I wanted to write, oh man, my tablet was working until just a minute ago. Got one of these newfangled MacBook Pros with the USB-Cs. It's not very reliable. The USB cuts in and out all the time. All right, great. So linear algebra for, this is what I wanted to write, fun and profit. So basically linear algebra is just the same as arithmetic, except that it's got multiple values per value. And those multiple values are called a vector. So yesterday we said a number line is kind of the most basic thing that you can use in math, and that every time you draw a graph, you're just picking a place on the number line to put the graph. All right, so this is called a scalar value. It's just one number. You could pick any one you want. I picked 2 there. I picked 0.5, which you could also write as 1/2. And I also picked -2 just because I was drawing those out. Okay, and there's rules of arithmetic that apply to these numbers that we all learned in algebra and pre-algebra and even before that, right? X plus y, X minus y, X times y, and so forth, like X over y or X divided by y. So we can deal with an additional number in our number line by drawing them as a vector, which we did yesterday. And it's still on a number line, except that the number line now has 2 dimensions on it, right? We're talking about this one here, 2, 2. And we can pick any point on this 2-dimensional number line, and we will have what's called a 2-dimensional vector. 2D vector, which is often denoted V. And people also like to put a bar over it, V, like that. Sometimes people put a caret over it like this, V, depending on what mood they're in. And sometimes they do it bold, V, to try to indicate that V is not just a number, but is in fact a group of numbers. Okay, we can have another 2D vector, Y. We could put a bar over it. But for this work, we're not really going to put bars over it. In my experience with all mathematical notation is that it's inconsistent. And everyone who works professionally in math gets a set of experiences through their education that inform how they like to annotate things. And they do those annotations in their papers or on their websites or in their research. And those annotations aren't the same as what anybody else does in their papers. So that's why I showed you that there are, excuse me, at least 4 different ways of writing vector, because it doesn't matter that much. People do it in a bunch of different contexts. Okay, but there are the same arithmetic rules about 2-dimensional vectors as there are about one-dimensional vectors or scalars, and more. There are more rules to two-dimensional vectors than one-dimensional vectors. And in my opinion, they're more interesting. I like to reason about them because they actually involve coordinates in space instead of quantities. Okay, a scalar, a number here, this is always a quantity. It's like an amount. And depending on what it is you're measuring, it could be any possible quantity, right? It could be a certain amount of milk. It could be the certain height of a tree. It could be a wind speed or a temperature from 0 to infinity. It could have to do with your altitude above sea level or your altitude above the center of the earth. It's very, very abstract how big a quantity could be. It could be all kinds of stuff, right? And in fact, that's the essence of data, is that each column in a spreadsheet is a different quantity, okay? But I like linear algebra because each point in this two-dimensional graph that we draw when we're doing two-dimensional linear algebra, we can have this point and this point and this point and this point. It's more than just the quantity, and it's more than just a pair of quantities. It encodes all these relationships inside of it as well that we're going to learn about a little bit here. Okay, so there are, like we learned yesterday, many ways of representing what I just drew here. Let's call this graph a little bit more zoomed in than we normally do. And it's got 1 is what we're looking at. We're zoomed all the way in to all we can see is 1. And this set of 4 points, we could write it out in a two-dimensional grid called a matrix. And the first one is, let's call it A. And the second one is down here, let's call it B. And the third one is over here to the left, and we call it C. And it's at -1, -1. And then the fourth one, D here, is at -1, 1. So let's examine that real quick before we move on. Okay, A is at position 1 in X and position 1 in Y, remember, because this is the X coordinate. And the coordinate, the names of these axes, they can be arbitrary, but they are very reliably called X, Y, and Z for the 4 axes. When people add a 4th dimension, sometimes they call it W, or sometimes they start counting from the top instead and they call the dimensions A, B, C, and D, but it is arbitrary. They are names. But the relationship, no matter what the dimension is named, the relationships remain the same. The relationships are what linear algebra is. And the names of the dimensions and the names of the points, those are just useful frames of reference that we use. Okay, so B is over 1 in X and down 1 in Y. So it's at 1 -1 here. C is back 1 in X and back 1 in Y. So it's at -1, -1. And D is back 1 in X, but it's up 1 in Y. So it's -1X and +1Y. So all of these points have relationships to one another. They're all a distance that we can measure from one another, and they're all combinations of one another as well. Okay, the most interesting thing about them, these are called basis vectors, and these are something that we will learn as part of our study of dimensions and the abilities that we have to reduce them mathematically. When we've got 10 dimensions, we can't visualize it. It's harder to use, and so we can bring it down to fewer. These are called basis vectors. Okay, and every set of points has a set of basis vectors. And in 2 dimensions, these 2 basis vectors are the most common ones that can exist. Now, it's possible to create a set of points in 2 dimensions that don't have these exact basis vectors. It's 1, 0, that is, you can go this way to the right in X, or it's 0, 1, you can go this way up. And every single value that exists in 2 dimensions can be built as a combination of these 2 basis vectors, which is a fun thing to study, okay? And we can do it with A and B right here. We can say that if we call this one this first basis vector in x, xb, meaning it's the basis vector that makes up the x dimension, yb is the basis vector that makes up the y dimension. Each of these vectors, A is equal to xb combined with xy, or yb exactly, and b is equal to xb minus y sub b. And all the points that can exist inside of this 2-dimensional space are just what's called a linear combination of the basis vectors of 2 dimensions. So I wasn't planning on jumping onto basis vectors at that time, but it's an interesting segue that I wanted to touch against. And we will come back to it in the main coursework. The most interesting thing about basis vectors is that when you have a bunch of points in a high dimensional space, they usually don't follow this neat structure. That is, they don't have a perfect distribution. A is not the same distance from B as B is from C as D as C is from D. I'll draw another picture of this real quick because the subject interests me so much. Okay, so imagine that we've got a bunch of points like this. So what happens in high dimension is that it turns out that the basis vectors for this particular pair of coordinates go this way and this way. See, because they're distributed in a diagonal. So the basis vector goes this way, and it goes up and to the right and up and to the left. And we're talking abstractly in higher dimensional points. And that each one of the points contained in that coordinate system doesn't actually follow this right-hand straight up rule. They have a different pair of relationships that we can discover mathematically that we'll get to in a little while. All right, so I want to talk about 3-dimensional axes briefly before we come back to the arithmetic of linear algebra, which we're getting close to. Okay, because we've done 1D drawings, those are easy. We've done 2D drawings, those are easy. And we've done 3D drawings a little bit yesterday. And they're not as easy because they are a projection onto a piece of paper, right? Humans, pick something up that's sitting on your desk that has a rectilinear shape, right? That is shaped like a cube or shaped like a rectangle. I have a few of them on my desk. I'm going to turn off screen share because I love props. All right, so this box of toothpicks has a rectilinear shape. It really doesn't look, it's elliptical on one of the axes, which is nonlinear, okay? But on this axis, it's straight. There's my x-axis. On this axis, it's straight. There's my y-axis. Look at that. There's our 2D graph. Look, pick a point on the 2D graph. There's one here, there's one here, there's one here. And then there's a volume too. And you could actually define a volume like this. It wouldn't be linear, but you could define in linear algebra, cheating it a bit, a volume called a manifold that has curvature in 2 directions. And the distance between points in this dimension would not be calculated the same way that the distance between points in these dimensions are, but it would still be a 3-dimensional space. So I'll go over to this one. This is another gimmick that I have. This one's even better. This is rectilinear as can be. It's all get up rectilinear. I'll show you what's inside too. Bought these like more than a decade ago and I've never used them, but they're so bling bling. They're like an accessory I keep to show off to the colleagues that never visit me in my home office. But you are now my colleagues that I visit in my home office. All right, so let's look at this again. We've got an x coordinate and a y coordinate, and you got to give it that perfect little rotation. A z coordinate, a depth that goes to and from the camera is usually how we deal with it. So we got x and y and z. And you can do this thing. This is called the right-hand rule. It's got all kinds of information encoded in it that we're not going to talk about today. But you can pick it up in your hand and go, look, it's a three-dimensional volume. And there are points. Pick a point, the bottom of the shield. Pick a point up there. That's the side of the shield. And then add a third dimension. Pick it in the middle. Okay, it can be on the face of it. It can be in the middle of it, or it can be on the back of it. And this is a volume. This is a three-dimensional volume. It's got its own coordinate system. I can do this to it. I can rotate it in this space. Here it is inside of my 3D space, which has a specific coordinate system. And now it has its own coordinate system inside of that. This is how computer games work, is that you just build coordinate systems inside of one another, and you can rotate models and build characters and all this stuff. All right, so going back to it. We drew two axes, and then we need that third one. And I'll dash it. It doesn't need to be dashed, but it makes it a little easier to visualize. Dash, dash, dash. Because it's passing through the volume. It's moving from you, away from you. And what do we got? We've got three coordinates, x, y, and z. All right, now I like to draw points in three-dimensional spaces because it's a very good mental exercise. All right, let's pick one. I'm going to go down and to the right because it's somewhat easier to occupy that space. Let's say -2 in x, -2 in y, and let's say plus, let's do +4, so it'll just be an even multiple of 2 in z. All right, and this is what? It's a vector named v. V equals -2, -2, 4. Now, how do we go there? We go back 2 in x, 1, 2. That's how far it is in x, but we're not done yet. We have to go down 2 in y. We're going along the axis here. 1, 2 to here. And now, this point still isn't quite there. This is located on the xy plane. We have to add 4 to it. Now, it looks like, because z is positive here, because I just wrote z, that means that this way is plus, and this way is negative. And that's not a guarantee. People mix it up all the time. And when you're working in multiple dimensions, you always have to ask yourself, what direction is positive and negative if you're trying to draw a visualization? So because I made this positive this way, we had this little intersection. Now we have to add 4 along z. So let's see how far they go. 1, 2, 3, 4. That's how far they go. Let's do it again from here, because this is 0 now. 1, 2, 3, 4. So this number turns out to be right about here. You can't tell because it's been projected. And this is a funny thing that you do in linear algebra. You take a three-dimensional point, like -2, -2, 4, and then you multiply it by something called a projection matrix, which is let me think about this. This one is 3 by 1, and that means that in order to turn this point into a two-dimensional matrix, we'll make this one 2 by 3, so it has 2 rows and 3 columns. We can just change it. This is the identity projection matrix. And what do we want to do? Probably just stick to the identity. So now we'll pass these numbers through. Oh, hold on, I drew a 3 by 3 matrix. That'll never do. Right, like this, 1, 0, 0, 1. Nope, that won't do either. Here we go. 1, 0, 0, 0, 1, 1. All right, now we'll get to this in a minute. This is matrix multiplication. We might as well do it now. The way that you multiply a vector and a matrix together is you pick this vector up, you tilt it on its side, you bring it over this way, you tilt it on its side so it's kind of shaped like this now. And then you slide it down through the matrix, then you multiply each row. So there's a formula for it. If we call this M sub ij, and we call this V, then the two of them together, m times V, is equal to B sub I times M sub, let's see here, M sub I 0 plus, I think I'm mixing myself up actually. We'll come back to this in a minute because I've got it written down on the next slide and I've got more that I want to cover. Let me see if there's any questions. I probably have students fixing my bad matrix multiply right off the top of my head. Vectors everywhere. Let's see what YouTube looks like. If there's anybody watching saying, what are you trying to do with that matrix multiply? Out of turn. Here it is. Hello, YouTubers. Abhinav is on top of it, as always. The answer is -2, 2. Thank you, Abhinav. Yeah, we are going in the right direction, aren't we? Okay, so then this becomes V sub, I'll call this 0, 0. V sub 0 times M sub, no, V sub 1 times M sub 1 plus V sub 2 times M sub 2. And then this one here is V sub 0 times, oh, I need my 2 dimensions, M sub 2, 0, or actually it's 1, plus V sub 1 times M sub 1, 1, plus V sub 2 times M sub 1, 2, which Abhinav calculated for us is -2, 2. Right, so then the projection didn't if I had made this negative, maybe it would have worked. The projection matrix that I've created right here actually drew it at this spot, which means that I had my projection matrix designed so that Z would go like this, and it actually projected almost exactly where it should be. And I will revise this because I think this is an awesome example. I'll revise this so that we can do a projection in class and it will not be wrong like it was this time. Okay, so 3D is cool. 3D is amazing because we can visualize the points contained within it. I'll draw it this way just because it worked that time so perfectly. Yeah, what I needed to do is probably, yeah, just make the matrix a little bit different. X, Y, and Z. All right, and any point, any number that we write out here, 1, 2, 3, 5, 6, 7, etc., fits into this space. It's in what's called R3, in 3-dimensional coordinates. Okay, but you know, when we're looking at a spreadsheet, things get out of hand really fast. Right, each row is one sample. Can't draw anymore. What's happened? Pictures? No, come on. There we go. All right, but the number of columns is the number of dimensions. And it very quickly becomes something that a human can't draw a picture of. Right? How often have you seen a spreadsheet with this many columns? All right, and I like to do temperature data like weather data, lat, lon, pressure, temp, altitude. Now we're up to 5 dimensions. What else could we put in there that's a weather thing? Oh, wind. And there's a multitude of wind dimensions we could put in there. Wind, gust, direction, and then even stuff like time of day. All right, so now what are we up to? 1, 2, 3, 4, 5, 6, 7, 8, 9 dimensions. in one sample, right? Here's my house, me, here's you, here's Abby, right? And so we have this humongous matrix full of 9-dimensional data. How do we visualize it? How do we figure out what it means? And that's the study of statistics, and more importantly today, machine learning, which is kind of like an applied version of statistics for solving certain kinds of problems. Where do we draw the fourth dimension? Where do we draw the fifth dimension? But more significantly, and this is what we're going to start getting into just now with the rules of linear algebra, is that these numbers don't occupy the same space, even though they seem like they do. So somebody, John, I have to jump in on this. The cross product only works in 3 and 7 dimensions. It doesn't work in any other coordinate cardinality. Isn't that strange? I'm sure there's some deep geeky math number science reason, but I don't know what it is. All right, so these numbers, what did I do here? Pressure. Let's just do these in atmospheres. That's easy. Temperature, do it in like C. I'm a Fahrenheit guy, what can I say? Altitudes, got to do those in meters, right? Because we're modern scientists. And what I'm getting at is that if we were to draw a graph of this, pick any two of these coordinates, draw a graph that's centered on O, the origin, 0, 0, 0. And it, unfortunately, latitude and longitude don't fit in the same space. Let's draw all the pressures. Here they are. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. They're all right there. So that's uninformative if latitude is all right here. Latitude, latitude, and latitude. And then longitude's way out here. So it turns out that we're only getting information from latitude and longitude because the pressure, the scale of pressure is teeny tiny. It only goes from, let's say, 0.8 to 1.4, which you might measure. You might measure your column of data and find out that its variance is small, okay? And then you might measure these. The range of this one is also very small, but has bigger numbers to it, 42 to 45 maybe. And then this one over here is 68 to 72. So you need ways to normalize the data, and you can do that using linear algebra. So here's the simple set of linear algebra lessons that I wanted to fly over. Most of them are very easy, and then we will end with the matrix multiply. We'll go back to this because it's actually the most important tool in machine learning today. And it's the most important tool in linear algebra, and it's the most important tool in video games. That's right, Chris. You can rescale them in a variety of ways. In your data prep as a machine learning scientist, you can go through your spreadsheet and define special rules for normalizing each column of data so that they enable your machine learning algorithm to be as successful as it can be. And I've told you this in the previous lessons, the vast bulk of your time, and today, the vast bulk of your time as a machine learning engineer involves fiddling with your data and fiddling with your model until it starts producing good results. And we're talking like, weeks and weeks and weeks and weeks of getting all your columns manipulated in a way that enables your algorithm to make the predictions that you want to make. All right. So these are in the machine learning pre-course work, and you can't get them wrong. All right. Let's say we've got a vector A, and we've got another vector B. We can add them. A plus B. Okay. And what happens is you think about not where the vector is relative to the other vector, but you think about where the vector is relative to this magical place called the origin, which is very, very important. The origin is the 0 vector. Oh, it equals 0, 0. in 2 dimensions. Okay, and A plus B, let's say that A here, we'll do a scale of 2 just because it's a little more interesting. It's 2 minus 2, and B is 2, positive 2. All right, and linear algebra is easy arithmetic. What are they equal to? They're equal to 4, 0, right? You just add them across. A sub I, we could define this like this. A plus B is equal to A sub 0 plus B sub 0, A sub 1 plus B sub 1, right? And that's arbitrary. You can write it out. This is a great way of writing it for better practice and visualizing your mathematical abilities. Take that. A plus B for 2 vectors is equal to A sub 0 plus B sub 0, A sub 1 plus B sub 1. And then you do this dot, 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 A sub n plus B sub n, right? Where n is equal to the dimensions of A and B, and they have to be equal. It's undefined. If A is length n and B is length m, can't add them together. It's not defined to do that. See you later, DJ Morse. Hopefully we'll be seeing lots of you in the upcoming coursework. All right, now the reason this is interesting, whoop-de-doo, oh, good job, Thompson, you're adding 2 numbers together at the same, or 4 numbers together at the same time instead of 2. Here's why it's cool. Okay, here's A, here's B, A and B, right? So the way it works is they are well, they're invertible. You can compose them either way, right? We know that A plus B, somebody can tell me the term for this because I forget. A plus B is equal to B plus A. So we can do it in any order. But A is not just a point in space, but it is a transition, or a translation is what it's called, from the origin. It's a line with a direction and a distance from the origin. So A is here, it's actually this bar. And when we add them together, B is translated by the bar A, okay, to here. So there it is, look, 4, 0, 4, 0. And so when we add the 2 vectors together, we are in effect translating or adding A to B. We've got B located here. We add A to it, which is related to 0, right? A's base relationship is fundamentally with the origin. So we add that relationship, this vector, out of the origin to B, which moves it to here. All right, so that's cool. And it works. We could have done it with B, right? Because B's vector is this one coming out of the origin. If we add B to A, right, plus B goes to here. This is A plus B, we say. A plus B is this one here. And then we can add A to B, which shoots it to the same spot. So I think that's really slick. And it's even better as you get into higher dimensions, the way that that works. All right, so we do the same thing with subtraction. Let's take on something that's a little less uniform for this one. A and B. And it works the same way. A minus B is equal to A sub 0 minus B sub 0, dot, 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 A sub n minus B sub n. Yeah. Make this thing big. Yep. All right, so what is A? A is 1, 1, minus 1, and B is, it looks like it's about 3, 1. All right, so what happens? Well, pretty easy to just do the arithmetic. Minus 2, minus 2. So what happens over here? This has the effect of changing the origin of A to BB. That's effectively, so how I want to express that. Maybe not. Let's draw minus 2, and see where that lands. Minus 2 is here. Did I do that right? Yeah. So what has happened is, here's B. It's a vector. It's not just a point in space. It's a direction and a length. A direction and a magnitude, it's called. And what we're going to do is we're going to take that direction and magnitude and we're going to subtract it from A, going back in the opposite direction, right? So A got moved to a position that was the opposite of B. A originated here and then slid back by the opposite of B to be located here. Now, this is really important because you move points around by adding and subtracting them, and you can change their relationships. Now, the best thing about it, this is the last thing I'm going to talk about, basic vector translation, is you do something called centroid adjustment. You change the origin of points. So you look at all these points here. These points have a confusing amount of information in them because they all have a high magnitude and they all point in this cone. Maybe I want that. Maybe I don't want that. And so what I can do is I can compute the average of all of these points by adding them up. And we just say the sum of v sub I is equal to, and then we'll multiply them by the number as well to get the average. The mean, v sub I, is equal to, scale them by n because there are n of them, times the sum of all of them. And what that does is it brings us to this center point here. And that's not really the mean, but it's close. Now if we take all the points v sub I, and we subtract them from this mean, we'll call it m. Well, it's popular to call it this, mu, the mean. So v sub I minus mu. If we subtract mu from all these v sub i's, they move to become oriented around the origin. And I'm just going to draw another cloud of points. I'm not going to try to copy them. All right, so now their individual lengths are meaningful relative to one another. And their individual angles, their directions are meaningful to one another. And that just gets me excited. I just love doing that, mean centering points. Now, there's one more crucial thing to do, and I'm going to fly through multiplication and division. Okay, you can take a point. 1's the easiest one to do. That's horrific. I've got to hurry to get to magnitude because magnitude's one of my favorites. All right, this point A is 1, 1. And if we multiply A by 2, which we'll typically just write 2A, right? You guys are getting better at math now. And so you know that you don't have to put a dot between numbers that get multiplied together. And you don't have to put an X between them. They just get multiplied. That's what it means for them to be together. 2A, multiply me. All right, and what's it equal to? Well, duh, it's equal to 2, 2. All right, and this is interesting because this is called scaling a vector. And if you've got a point out here and you multiply it by a scale, well, that scale gets really big really fast. Zoom, it shoots away. But if you subtract it back to the origin first, put it here, and then multiply it by a scale, then you can take a group of points and change their shape using multiplication. All right, the same thing goes for division. B. That looks like a 3 minus 2 to me. All right, and division, it's much easier to write it out. We could call this V. And we could say that we want to know what V divided by 3 is. All right, and we can do that. The easiest way to do it, and the best way to do division, now that you're a mathematician, is to just multiply by 1 over the number you're trying to divide by. That's really what division means. It doesn't mean divide by or what's the remainder. It just means multiply by the inverted fraction of that number. All right, so that's pretty easy, right? Then we get 1 and minus 2/3. And that's the new position of this. Oh, what did I do here? up 3. Oh, I inverted my axes. Let's just redraw this, since it's easier to redraw this than to redraw all that stuff. Okay, so I divided it by 3. Well, what happened was we took the length of the vector. You see how long it is? We chopped it into thirds, and then B became the third element there. Cool. All right, final thing before matrix multiplication. Is this entertaining? Have you all seen this before? It's entertaining to me. Okay, and now finally, my favorite thing to calculate about a vector is called its magnitude, because it actually presents you with a huge amount of information, and it gives you a real profound level of control over the data compared to not knowing it. Once you know the magnitude, you can store that separately, and you can go nuts on V and learn all kinds of new things about it that you did not know before. I shouldn't write V sub I over here. Scribble V. Got to erase it. I'll never get back, will I? Yeah. Close enough. All right. So this is something that you have been presented with in your pre-coursework. The magnitude of V is equal to the square root of the sum of all the elements I of V over its entire length, V sub I squared. All right, so let's draw a picture of one. And the very best one to calculate the magnitude of is the vector 1, 1, A. A equals 1, 1. And the reason that it's important is because what do we want to do? We want to get the square root of 1 squared plus 1 squared. That's what this expression means. It means exactly what this expression is. Same thing. If we had more elements, let's make up a different one. B equals 2, 2, 2. Then its magnitude, the magnitude of B equal to square root of 2 squared plus 2 squared plus 2 squared. Right? All right. Pretty straightforward. Now, what is this magnitude of A equal to? Well, it's equal to the square root of 2. Okay, so the magnitude of a vector with exactly one element of the x basis vector and exactly one element of the y basis vector, 1, 1, its magnitude is not 1, it is 2. All right. So look, we get a vector like this. I want to go to the next page. And so now we know how to calculate the magnitude. Now let's reason about the magnitude a little bit. And I'm going to use the whole page for it because it's fun. All right, so we've got this vector A. We're familiar with A. A equals 1, 1. Let's make this vector B out here. It's much farther away. It's minus 5, 5. And we'll do C as well, just because we need that information. C is minus 5, minus 5. Okay, so the magnitude of A is the square root of 2. The magnitude of B is the square root of, right, minus 5 squared plus 5 squared equals what? The square root of 50. All right, and here's the punchline. The reason I wanted to do C also. The magnitude of C is also the square root of 50. Because the negatives don't mean anything. That's why we square them. Because the magnitude cannot be a negative. It's always a positive. And it always measures how far the vector is from 0. How far is this vector away from 0? Or how long is it Or how forceful is it? Okay, 50. And you could say that it is D, the distance from the origin, D equals 50. Or you can say in one more way, right? Magnitude of C equals 50. What's the square root of 50? What's the square root of 50? 7? Yeah, it's just over 7. All right, so if we were to tick this out, here's what we'd find. Exactly length 1 falls about here. It falls right at the square root of 2. Length 50, we go like this. Tick, 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 tick. Oh, look at that. It's exactly 7 ticks away from the origin. This one too. 1, 2, 3, 4, 5, 6, 7. Look, it's length 7. Here's where things get interesting. We say that C divided by its own magnitude is equal to a very special vector, which I don't even have a notation for, and there must be one. If somebody knows it, tell me. It's called a unit vector. It's the unit vector of C. And a unit vector is, by definition, a vector whose magnitude is 1. The magnitude of a unit vector is equal to 1, okay? So the simplest unit vector here, you can have a unit vector like this, 1, 0. You can have a unit vector like this, square root of 2, square root of 2, which you also write, it's about 0.717. I'm just going to write 0.71, 0.71, 0.71. All right, these are unit vectors because if we calculated their magnitude, they would be equal to 1. And the cool thing about a unit vector is that it prescribes a thing around the origin called a unit circle. Every unit vector falls upon this unit circle together. So if we take a group of points and we all compute their normals, we compute their magnitude, and then we divide by that and turn them into normal vectors or unit vectors, then instead of containing a distance, D, and a direction, they only have a direction now. And we can learn from them things like, do they go away from the origin in a group, or are they evenly spaced around the origin, and so on. It just gets me riled up to do this with two-dimensional points. You can do it with higher dimensional points. Okay, so the last trick, it's 6:58. I didn't expect that my final session would be the longest, but turns out I'm enthusiastic about linear algebra. It's silly. The last thing that we do with vectors is we multiply them by a thing called a matrix. Matrices are amazing. And I even prepared this because I'm so enthusiastic about talking about it. I remember when light bulbs went off in my head in grad school involving linear algebra in this way, I felt like I'd seen the light. All right, so remember we talked about this one. Here's a vector 4, 4. It leaves the origin and it goes up to 4, 4. Okay, now imagine we've got a cloud of random points. These random points go from 0 to 1 in x and 0 to 1 in y. But we can zoom out. Look, let's zoom out on them. Now this plot goes from -10 to 10, and these plots don't look like they're as spread out as they used to. Okay, but they're exactly the same points, exactly. The only thing that we are seeing different about them is how far away we are when we look at them. And the interesting thing about that is that if we multiply them by another number using vector multiplication, we can make them look the same again, even though the values are totally different. It's all a trick of matrix multiplication. Every picture of dots that you see is a trick of matrix multiplications. Every game, every movie animation, every graphic that goes across the screen while you're watching sports is just somebody multiplying some points by some matrices that translate them. So what I did here was I said, give me that same matrix. I made a new one because I'm going to modify it directly. And I did something funny. I did something called, I added homogeneous coordinates to it. So we're going to print x. X is really just 2 dimensions. But I added a third dimension called the homogeneous dimension. And what this does is it lets me use a matrix to translate the points. That's all it's for. All right. Now I've created a matrix that's three-dimensional here. I'll print this one too. I called it sub because it's a subtraction matrix. Here's what it is. It's got ones along the identity, along the diagonal, but it subtracts 3 from x and it subtracts 3 from y. And I do a thing called a matrix multiply, and this is what graphics cards do. It's the only thing that they do is multiply a point in 3 or 2-dimensional space or higher by a matrix. Okay, so we've got 20 points that are random, containing a homogeneous coordinate so that we can add or subtract from them, and we multiply them together. It's the same points that we're looking at here. See how they're between 0 and 1 on my little graph that's not perfectly scaled? It's much easier to see it here, between 0 and 1. If we multiply them by this matrix that has a -3 here and a -3 here, all 20 of them instantly move 3 down and 3 back. See, now they're oriented around -3, -3, and -2, -2. So we translated them with a matrix. You can do a lot more with a matrix. You can scale with a matrix. Let's change this. I want to make my x-axis bigger by 2, and I want to make my y-axis bigger by 3. Now the points have become spread. Let's make the y-axis even bigger than that. Let's make it bigger by 7. So we're expanding the points, we're massaging them and manipulating them. And all we do is manipulate by this matrix. Okay, and I was going to do a rotation. Okay, a rotation is another simple thing that you can do with a matrix that does linear algebra on the points and moves them around, but we are out of time. So I'll take questions. I will be quiet for a while. I'll take a drink of water. I've been talking about linear algebra for like 40 minutes without a drink. The reason I like linear algebra is because I can visualize it in my head. And when I got good at it, now I'm not as good at it as I was. 10 years ago, I took, I want to say, 4 different PhD level linear algebra classes where we did hilarious tricks with it. And I got to this stage where you could write a matrix out for me and I could visualize the shape, like I was showing you my brush picks. I could visualize the shape of that space in my head and rotate it and add other matrices to it and that sort of thing. So Jack, what way does the Z-line go? It's arbitrary. It's frequently arbitrary. Well, it's always arbitrary. And what you hopefully find is that when you work in a specific industry, say if you were an electrical engineer, you guys would have a specific set of rules that you learned in academia and in your professional career that you settled on. And when you read somebody else's notation, most of the time it would be safe to assume that their z-axis, that is plus coming toward you or away from you or being in the lower left quad versus the lower right quad, would have been agreed upon by some pre-existing handshake that you never even made with anybody that, like, you know, your boss's 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 boss made. And so every industry is divided and there is no uniform rule. You know, the very worst thing about it is, consider this computer graphics screen. Okay, computer graphics screens, this is where the origin is. It's right here in the top left. And it goes down in the y-axis and right in the x-axis. And computer graphics pictures, like this one here that got rendered by Collaboratory, they start in the bottom left. And so x still goes to the right, but y goes up. And there's just tons and tons of this freaking absurd inability of humans to collaborate about anything at all. Yes. So Hashiba, I would love to answer your question, and I will. And it's a pile of worms. But so I'm going to answer Richard first. There is a Khan Academy course on calculus that is easy and smooth, that is enjoyable. And there's a guy, oh gosh, I want to bring him up. Give me a sec. There's a guy who makes some brilliant tutorials on YouTube. What's his name? Gosh. I'm gonna search my own YouTube history to find his name, because I should have access to this guy, because I think he's got some calculus lessons too. I've also recommended that you do Google's machine learning crash course they just released, which is pretty awesome. It's got some really cool tools and widgets that we will be playing with in class, because I'm not going to code one. Yes, three blue, one brown, Richard. That's who I'm thinking of. Three blue, one brown on YouTube has some mind-blowing YouTube videos. And three blue, one brown even has something on thinking visually about higher dimensions. I'm going to watch that tonight. There's a different YouTube video on high dimensions that was narrated by this young boy who's like a 15-year-old teaching us how to visualize 11 dimensions. And that one was really very good too. Yeah, I mean, there's tons of them. I don't have a best recommendation. Frankly, I would like to go back to college and take Calc 2, Calc 3, and differential equations again. But in my experience, you might be better off than me, but in my experience, I only really learn calculus by doing it for 4 hours a day, and I just don't have the time for that anymore. Fahad, I don't think so. I think you're referring to like GraphQL. You might be talking about graph algorithms, which there are some things like hidden Markov models that utilize graph decision making and decision trees, but we won't be doing a ton of it in this course. It's going to be mostly kind of regression driven. It's going to be primarily concentrated around the neural network, which has been whooping the butt of all the other machine learning algorithms recently. Okay. Oh, Hashiba. I'll give you a very, very quick description of how to parallelize an algorithm. We will have at least 1 week in the full-time course dedicated to algorithm parallelization, but it's heavy stuff. Okay, the way that you parallelize an algorithm to run on multiple machines is you identify periods in time in the algorithm's execution that do not depend upon one another. You say, oh, at time equals 4, all the values inside of this computation that I'm doing only depend upon the values that came before them, and they don't depend upon their neighbors. They don't depend upon the values that were computed now. So I will separate out my calculations so that each tree or chain of dependent calculations goes onto one GPU. And then at time equals 4, they will all come, or at time equals 5, perhaps, they will all come back and recombine their calculations so that they can continue on to time 6, 7, and 8, which aren't dependent on one another, and then they'll reconvene again at time 9. That's the essential process for parallelizing an algorithm, and it's difficult to describe in mathematics, and it's even more difficult to implement. Thanks for coming, everyone. I want to remind you one more time to go to the ML pre-course GitHub repository. That's all the tests. And then send me a pull request of those tests. And let's see here. Here's where the pre-course material is, YouTube listeners. Oh, I cannot share with you a YouTube address. It's weak. It's the ML dash. Here, maybe this will work. That's funny that I can't share a URL on YouTube. I am the school/ML pre-course on GitHub to get that. And If you're not in the course yet, oh, here, it's really funny. It just now took away my ability to share web addresses. So go to lambdaschool.com. And sign up, and I'll see you in 2 weeks. Christopher, I think I have your pull requests. The original repository, I made it auto-execute on Travis, and I'm hoping that I can hop into my Travis instance and allow it to run all the pull requests so that I don't have to pull them down and check them manually. Thank you for your kind words. I did teach CS for a while, and it was fun. And I got moved on to this because I'm one of the only people who can. Turns out, you know, I almost got a PhD in machine learning 10 years ago, and machine learning's so hot right now. Thanks, everybody.